Good morning to everyone. All of you can able to hear me well?
Yes, sir. Good morning, sir.
Good morning. Okay, and today I'm going to start with today I'm going to start with modulus 10, modulus 10 synchronous counter, modulus 10 synchronous up counter. Okay, so how do you design that? What is the first step? Okay, what is the first step? Should find out how many number of flip-flops are required. So this is nothing but 10 modulus 10. What is the meaning is 10 different states are available. 10 different states are available. So in order to get 10 different states, how many number of bits are required? For example, if we take 2 bits, what happens? I will get only 4 states. If I consider 3 bits, what happens? I will get only 8 states. Okay, suppose I am taking for 4, what happens? I will get 16 states. So what is the formula for this one is n less than or equal to 2 power n. That is a formula. So what is the meaning is I record 10 state. The 10 is less than or equal to 2 power 4. That is nothing but 60. So now condition is satisfied. So how many number of bits are required? How many number of flip-flops are required? A number of flip-flops are required 4. Is it okay for you?
Yes, sir.
Okay, that modulo 10 flip-flops, otherwise called as otherwise called as decade counter or otherwise called as a BCD counter. Decade counter or otherwise called as a BCD counter. Okay. Okay. So what is the next step? So what is the next step? Okay. I should write step 2 should write state diagram for given problem. State diagram for given problem. Okay, so initial state is 0. Okay, okay, what happened? Keep on increasing. Next step is 1, 2, next one is 3, 0, next one is 4. Okay, what do you did at 4? 0, 1, 0, 1. What about next one? 6. Okay, what about 7? This is a 7, 1, 1. And what about 8? This is a 8. What about 9? This is a 9. This is a synchronous up counter. What happens? Keep on increasing the value. Whenever the value is this is a 2. 5, 6, 7, 8. So whenever the 9 is okay, again what happens? You should go to the beginning of this. Okay. Okay. So what is the next step? Any one of you tell me what is the next step? Okay. Here, what type of flip-flop I'm going to consider means I'm going to consider uh, T flip-flop. That is called as a doggle flip-flops. Okay. What is the excitation table on the doggle flip-flops? So, 3. Okay, this is a Q1, this is a Q1 plus 1, this is nothing but state. So 0, 0, 0, 1, 1, 0, 1. Okay, what happens, sir? I want to retain same state. The input is 0. Okay. Um, okay, I want to double the input. What happened? So what is the input? So previous state is 0, next state is 1. Is the current input 1? Okay. Again double 1. Okay, again I want to retain same state. So there is a excitation table of T double flip-flop. Okay, what is the next step? You want to form. Want to form minimize the Boolean expression from excitation table. Okay, state and next state. So already I said, so in order to design a model of 10 flip-flops, it's needed 4 flip-flops. Okay, each one of them what happen is going to generate the output. That's why the state is a 4. 2, 1, 0. So okay, this is a present state, this is a next state. What is the next parameter? Record input. Yeah. Okay, so record input is T3, T2, T1, T0. Okay. So this, okay, first what happened? What is the state for initially for all the flip-flops? Okay. Okay, how do you fill up the table? So based on the state, initial state is a 0, 0, next state is 0, 0, 0, 1. Okay, this is a the previous state, the next state is acting as the next. Okay. So initially, this is the first clock cycle. Okay. This is a 0, 0, 0, 0, 0, 1. Okay, what about next one? The next state for the next clock cycle is acting as result state. Okay. So the label of the table 1, 0, next one 1, 0, next one, 1, 1, 0, 0, 1, 0, 0, 0. This is a 3, this is fourth clock cycle. This is acting as a current. This is acting as a current present state. Okay. What about next state? The next state is 1, 0, 0. Okay. The clock cycle what happened? 1, 0, 0 is acting as a present state. 0, 1, 0, 1. What about next one? 0, 1, 1, 0. The seventh clock cycle what happened? 0, 1, 1, 0 is acting as a present state. So what is the next state? Next state is 0, 1, 8, 0, 1 is acting as a present state. The next state is 1, 0. What about ninth clock cycle? The ninth clock cycle what happened in the sense 1, 0, 0, 0. Okay, 1, 0, 0, 1. Okay, whenever the 10th clock cycle what happened, it will reach the same state. Okay. So why it is called as a BCD counter in the sense? What is the meaning? How we are going to perform BCD addition? Suppose I had the two numbers 4, 4. I had the two numbers. 4, 4. Whenever you are going to perform addition, there is no problem. Okay. So what is going to produce? There is the output. Suppose my resultant value is greater than 9. So what happened? Whenever the resultant value is greater than 9, what happened? You're going to add correction bit that is nothing but 6. So then only what happened? You're going to produce as a correct result. What is the meaning of BCD addition in the sense? The values appear from only from 1 to 9. That's why it's called as a BCD counter, otherwise called as a decade counter. Okay. So now we got the state. Okay, how do you fill up the table? Any one of them tell that. Okay, the present state is a 0, next state is a 0. What happened?
0.
0. So based on that, you tell the value. What is the next state?
0.
0. Next.
0.
0, 0. Okay. 0, 1. Rest of the places, value equal to 0. So what about next one? So 0, 0, 1. 0, double 1. 0, 0, 1. 1, 1. 0, 0, 1. 0, double 1. 0, 0, 1. 1, 1, 1. 0, 0, 1. 0, 0, 1. Okay, this is a value. Okay, so how we form the Boolean expression? So now we got the record table values. Okay, this is a treated as output, and present state is acting as input. Based on the product, we are going to be using it. Okay, this is a four variable column. So what happened? So you are this is a four variable function. So for that you are going to take four variable column. 1, 2, 3, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. This is called as a Q3, Q2. This one is called as a Q1, Q1. Okay. So look at the table. So what are the places we had the values? 1, here 1, here 1. Okay. Okay. This is a 1 and this is a 1. Okay. So this is a 1, the value equal to 0. 2 also 0, 3 also 0. So what about 4? 4 also 0. This is a 5, this is a 6, this is a 7. 8 equal to 1, 8 equal to 1. What about 9? So 9 equal to 0, sorry, 9 equal to 0, then 1. So what about the rest of the cases? Uh, okay, what about rest of the cases? 11, 12, 13, 14, 15. So these are the places you don't have value. That's why you're going to treat it as a don't care condition. That's why what happened, I'm going to fill it as a don't care condition. Okay, it's now okay for you. Okay, you don't have value for 11, 12, 13, 14, and 15. So these are the places what value we are going to consider in the sense. Suppose you don't have the value in the sense, that place you treat it as a don't care condition. So that's why I filled the rest of the places don't care condition. It's okay? It's okay for you?
Yes, sir.
Okay. And now you perform grouping. So here quad grouping is possible, here path grouping is possible. If you do the initiation, this is a value Q3, Q0. Okay, do it yourself. Can you check whether you got this answer or not? Okay, this is a value. Try it for next combination. What is the next one? You take this is for T2. Next you take T2. Okay. So how do you form a Boolean expression? Okay. Try it out yourself. Q3, Q2, Q1, Q0. 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. So what are the places output plan equal to 1? 1, 2, 3, 4. 0, 1, 2, 2, 3, 4. Double 0, double 0. What about next? Next one is 8, 0, 1, double 0, 0, 1, double. Okay, 1. Okay, so rest of the places value equal to 0. Don't need to fill up the 0. Okay. So what is the value of 10, 10, sorry, 11, 12, 13, 14, and 15? So we don't know the value for those bits. So that places what happened, we are going to fill it with the don't care condition. So next you form a grouping. Here quad grouping is a possible. If you do that, what is the value? So value is Q1, Q1. Okay. So okay for you? It is okay. Do you have any queries? Let me know. Say yes or no. You try to
No, sir.
next combination. So what is the next combination? So sorry, P2, P1. So P1. Okay. Okay, what are the places output value equal to 1? You take the respective input values. Okay, go to the T1. Okay, and consider what are the places output value equal to 1. You take the respective input value. Okay, and fill up into the table. So if you do that, what happens? 1, 1, 1. Okay. So then 11, 12, 13, 14, 15. We don't have the values. That's why I treated as a don't get condition. Okay, and then you should perform grouping. Okay. If you do that, this is a value. Okay, what is the value of what is the Boolean expression for T1 is Q3, okay, Q3 bar Q0. Similarly for T0, okay, if you do that, okay, what are the places output value equal to 1? You take the respective input values 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, so you consider the T1, T0, all the places values are 1. Okay, so what I'm going to do, I'm going to write all the places values are 1, 1. Okay, but we don't know value of 11, 12, 13, 14, 15. So those places what I'm going to do, I'm going to fill up with the don't care condition. Okay, don't care condition. Okay, the next you start the minimization. If you do that, what happens? Okay, here what happened? Uh, so all the places are values are 1. Here don't care conditions are available. Here what I'm going to do, I'm going to consider don't care condition value equal to 1. If you do that, what happens? The T naught value equal to 1. Okay, it's okay. Okay. So now successfully we form minimized Boolean expressions such as T3 equal to Q3 Q naught plus Q2 Q1 Q naught. Next T2 equal to Q1 Q naught. Next T1 equal to Q3 bar Q naught. The T naught equal to 1. Okay. So in order to designing BCD counter, it's require 4 flip-flops. It's require 4 flip-flops. Okay. Uh, 1. It's require 4 flip-flops. 1, 2, 3, and then 4. It's require 4 flip-flop. This is a synchronous counter. Synchronous counter in the sense uh, all the clock pulse, all the flip-flops, we are going to apply same clocks. All the flip-flops, we are going to apply same clocks. That's why it's called as a synchronous counter. And this is the first one, T0, Q0, T1, Q1, T2, Q2, T3, Q3, and this is for Q1 bar, this is for Q1 bar, this is called as a Q2 bar, this is called as a Q3 bar. Okay. Okay. So what is the input for T1? T1 is 1. So what about sorry, T0? T0 value equal to 1. So what about T1? T1 is nothing but Q3 bar, Q3 bar, and then Q0 bar. Okay. So now what I've done, okay, this is a okay, Q3 bar, and then next input is Q0. So what happens? It's going to produce output as Q3 bar, Q0. Okay, this is the input for T1. So what about next one? T2. So what is the input for T2? Q1, Q0 bar. Q1, Q0 bar. Q1. This is a Q0, and then Q1. Okay, this is the input for T2. So what about T3? So T3 input is Q3, Q0, and then Q2, Q1, Q2. Okay, this is the input for one AND gate, and this is the input for another AND gate. Okay, and then it's require one more OR gate. Okay, the output of OR gate is input for T3. Okay, this is a logical diagram for modulo stem synchronous counter, otherwise called as a BCD counter, or otherwise called as a decade counter. Okay, now what happened? I implemented using T flip. Suppose you are going to implement JK flip flop in the sense you will get some other logic diagram. Okay, and then so both of them it going to produce the same result. Okay, so do you have any queries? Do you have any queries?
No, sir.
Okay. Okay, you will try it out yourself. I will provide certain problem. Okay, you will try it in your home. Okay, so design. So after completing my class, I will share all the materials. So every problem is available in the shared material. Okay, you will try it out yourself. After that, after sending the material, you will cross check whether you work it out properly or not. So design synchronous mod 6. So mod 6 down counter. Okay, how do you designing that? So in order to designing that, how do you do that? If suppose I'm taking 2 bits, what happen? How many number of states are available? 4. If you take 3 bits, what happen? 8 states are available. So what is the condition? 6 less than 8. The condition is satisfied. So in order to designing this, that above problem, it's require, okay, it's require 3 flip-flops. Such a way that you want to do that. Okay. So I will provide a hint. How do you do that? How do you solve this problem? Okay. This is called as a down counter. Okay. Down in the sense what happened? So how the state diagram is look like in the sense initial state is a 0. How many number of states are available? So initially 0 0. After that what happened? 0 7 6 5 4 3. Count how many number of states are available. 1 2 3 4 5 6. When it will reach the 3, what happened? Okay. So what happened? So whenever after reaching third state, what happened? So suppose you are going to apply one more clock cycle, what happened? It will reach again same state. Okay, such a way that the diagram should be appear. This is a 7, initial state is a 0, 6, 5, 4, okay, 3. When we reach the 3, again what happened? Again, and once again you apply one more clock cycle, what happened? It will reach same state. Again, what happened? It will reach starting state. Okay, so such a way that state diagram available. Based on that, you will form excitation table. and then from this you will derive Boolean expression. Okay, it's okay for you. You will try it out yourself. Okay. After that, I will send the material. Okay. Okay. Next, one more problem. This is first problem. The second problem is so design synchronous mod 6 up counter. Up counter. Okay. So up counter in the sense what happened? So how many number of states are available? Up counter in the sense, first of all, how many number of bits are required? Anyone tell that? How many number of flip flops are required? How many number of flip flops are required? Or you understand or not? Say yes or no.
Yes, sir.
Okay. So it's in order to implement that concept, it's needed 3 flip flops. So 6 less than or equal to 2 power 3. So condition is satisfied. So 8. Okay. How many number of states are available? This is up counter. Up counter in the sense, how do you do that? 0, 1, 2, 3, 4, and 5. So once after reaching the 5, suppose you are going to provide a one more clock cycle, what happens? It will reach starting state. Okay. Then this is idea. So based on that, you will do that. Okay. The next problem is I will work it out. Okay. This is a two problem. Okay. You want to solve it yourself in your book. Okay. Okay. Next, the last one is okay. You want to design want to design a counter that goes through the state 03560. Okay. So how do you do that? Okay, here how many number of states are available? 0356. Okay, in order to designing this problem, I need 3 flip-flops. Suppose I am taking 2 in the sense what happened? Only 4 states are available. 0, 0, 0, 1, 2, 3. Here 6 and 5s are available. So in order to get 6 and 5, okay, so n values are nothing but 3. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. So number of flip-flops required is 3. So what about state diagram? So initial state is a 0, 0. So after that what happen? Let's keep on increment. The next state is 0, 1, 1. What about next one? The next state is 1, 0, 1. Okay. This is a 5. So what about next state? The next state is 1, 1, 0. This is called as a 6. Again what happening? It will reach starting state. Okay. This is a state diagram. So how I'm going to implement this concept means I'm using for, you can use any one of the flip-flops. In the real world, different type of flip-flops are available. JK, data flip-flop, toggle flip-flop, data flip-flop. Okay, for the implementation, you can use any one of the flip-flop. So in my problem, what happened? I'm going to use so data toggle flip-flop. So what is the state excitation table of toggle flip-flop? So 0, 0, 0, 1, here 1, 0, 1, 0, 1. So 0, this is a 0. So 1, 1. This is a excitation table. So what is the next thing? You want to form minimize the Boolean expression from the excitation table. Okay, okay, how many number of states are available? Present state and next state. How many number of inputs are required? Required input. So this is a 3 Okay, we are going to implement that concept using 3 bits. So totally 3 flip-flops are Q, Q2, Q1. So what about the input T2, T1, T1? Okay. So initial. Okay. So how do you fill up that state? Based on the state diagram. 0, 0, 0. What is the next step? 0, 1, 1. Okay. The next state, then the next clock cycle, it's acting as a present state. 0, 1, 1, 0, 1. Okay, what about the next one? 1, 1, 0. What happened? Again 1, 1, 0, 0, 0. Okay, it's okay. புரியுதா நான் புரியுதா
Yes, sir.
Okay. Okay, அவ்வளவுதான். So you apply the excitation table. So 0, 0. What happened? What is the input?
0.
0, 0, 1, 1, 1, 1, 0, 1, 0, 1. Okay. So what about next one? 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1. So what about next case? 1, 0, 1, 0. Okay. So now successfully fill up the table. Okay. So how many number of outputs are available? 3 outputs are available. One name we called it T2. Okay. Okay. How do you mean me saying it? This is a 8 variable and 3 variables are available. How many number of input combination? 8. That's why I go for 3 variable column. Q1, Q0, 0, 0, 0, 1, 1, 1, 1, 0. Okay. If you fill up the table, what happens? Here 1, here 1. Okay. So what are the values not available? 1, 2, 4, 7. Now, these are the places what you're going to do. You fill up with don't care condition. Okay. So where 2 is available? Where 2 is available? Here, don't care condition. What about 4? Okay. Here, and here. So these are the places you fill up with the don't care condition. So what is the next step? You want to perform grouping. If you do that, what is the value? T2 equal to Q2. Okay, you will try it out yourself. What is the answer? Okay, Q1. So, next time taking for T1. Q2, Q1, Q0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, if you fill up the table, what happens? Okay, it should be appear like that. And then these are the places 1, 2, 4, 7. What happened? You don't have the values. That's why you fill up the value with don't care condition. Okay. So don't care, don't care, don't care, don't care. Okay, if you okay here what happened? For all the places fill it up through 1. The rest of the places what happened? Don't care conditions available. Okay. You consider don't care condition value equal to 1. If you do that, what happens? The value is nothing but 1. Okay. The last case T naught. Okay. Okay, T naught 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, this is a 1, this is a 1. These are the places what happen. I'm going to fill up with the don't care condition. Okay. So quad grouping is possible. If you do that, the answer is Q1. Okay. Okay. So what is the state diagram? What is the logic diagram? Okay. How do you draw the logic diagram? Okay. Okay. In order to implement this concept, it's like Q 3 flip-flops. Okay. What is the value of T2? The T2 is nothing but Q1. What is the value of T1? 1. What about T naught? The T naught equal to Q1 bar. Okay. So T naught, Q naught, T1, Q1, T2, Q1. Yeah. In order to operate the flip-flop, it's needed clock pulse. You can provide any one of the clock pulse, either positive or negative. In both cases, it going to produce the same result. Q1 bar, Q2 bar. So what is the value of T naught? The T naught is Q1 bar. Q1 bar. Okay, what about T1? 1. So what about T2? T2 is Q1 is acting as input for T. Okay, from this, okay, I will derive, I will provide the definition of, okay, this is a logic diagram for given problem. Do you have any queries? Larga queries, do you have any queries?
No, sir.
Okay.
No, sir.
So based on that, what happened, I will derive certain definition. The first definition is called as self starting state. Self starting state. So what is the meaning of self starting state in the sense? A given problem. So for example, you want to designing mod 6 up counter. Okay. How many number of states are available? Start with a 0 and keep on increasing 1, 2, 3, 4, 5. Okay, once it will reach 5, after that you provide any clock, any one of if you provide a next clock cycle, what happens? It will reach starting state. So what are the states are left? 6 and 7. Okay, 6 and 7. Suppose, suppose, suppose I am there in the second state. If suppose I am going to provide a one clock cycle, what happen? I will reach third state. Again, I will provide the next clock cycle, what happen? I will reach fourth. So one more clock cycle provide, I will reach fifth. Again, one more clock cycle I will provide. Again, what happen? I will reach starting state. Okay. Similarly for the rest of the state. Okay. So what I am trying to say there, suppose I am there in the 2. So suppose I am in 1 in the sense, if I provide a number of clock cycle, what happen? I will reach starting state. There is no problem. Suppose I am there in this and the 6th state. Suppose I am there in the 6th state. Okay. Suppose we move on to 6 and 7. 6 and 7. Okay, we want to any one of the state, any one of state. Suppose I am going to provide a number of clock cycle, we can return to starting state of the counter. We can return to starting state of the counter. For example, the diagram should be appear like that. என்ன பண்ணிருக்கேன் 6 7 வரைஞ்சிட்டு again starting ஸ்டேஜோட கனெக்ட் பண்ணிருக்கேன். சப்போஸ் I am there in the 6, நான் ரெண்டு கிளாக் சைக்கிள் கொடுத்தேன் அப்படின்னா I will reach the starting stage. Suppose I am 7, I will provide single clock cycle. In the sense what happen, I can able to reach starting state. If it is there, the entire diagram we call it as self starting state. The entire diagram we call it as self starting state. Okay, do you have any queries? What is the self starting state? So do you have any queries?
No, sir.
No, sir.
இது given diagram, அதே மாதிரி இதுவும் given. நான் ஏதோ ஒரு ஸ்டேட்ல இருந்து என்னால் ஸ்டார்டிங் ஸ்டேட் மூவ் பண்ண முடியும் அப்படின்னா அந்த டயக்ராம் பேர் என்ன அப்படின்னா செல்ஃப் ஸ்டார்டிங் ஸ்டேட். ஓகே, ஸோ the next I will define one more definition, that is called as a lockout problem. So what is the meaning of lockout problem in this sense? So I consider previous problem 0. These are the states are available 0, 3, 5 and 6. So what are the left out states are there? So 1, 2 and 4. Okay, 1, 2, 3, 4. Okay. These are the states are available, assume 1, 2 and 4. So here, which one is the starting state for the given problem? 0. Okay, this is the starting state. Okay, suppose I am there in the third state, I can able to reach starting state for n number of clocks. Okay, I can able to move it. Okay, suppose I'm there. Suppose we move on to, suppose we move on to 1 to 4 for any one of the state. Any one of the state, any one of the state, we are we are not able to return the starting state of, or we are not able to return original starting state starting state original starting state. For example, they okay. So already we have seen one of the problem. In a part of, we want to we want to designing the counter. These are the states are available. We have seen 0, 3, 5, 6 பார்த்தோம். அந்த ப்ராப்ளம் எடுத்து பார்த்தீங்கன்னா உனக்கு தெரியும். நீ எந்த ஸ்டேட்ல இருந்தாலும் என்ன பண்ணலாம் அப்படின்னா ஃபைனலா ஃபார் n number of clock cycle வரப்ப you can reach initial state. So what are the state அதில் left பண்ணியிருந்தோம்? 1, 2, 4, 7 left பண்ணியிருந்தோம். Suppose I am there in the second state. For any number of clock cycle, I am going to provide, but I am unable to reach starting state. So if it is there, the entire diagram we call it as locked out problem. It's okay. It is okay for you.
Yes, sir.
Yes, sir.
Okay. Okay. So remaining thing we will see next class. So now I'm going to take the attendance. Now I'm going to take the attendance. Don't leave from the classroom. Okay, thank you so much. If you had any queries to be stay on online, otherwise you can wind up the session.